So yesterday we worked with, or last class I should say, we worked with the graphs of logarithmic functions. We talked about them in terms of a transformation. So now we'll look at writing the equation of a logarithmic function given this graph. So if you look at this, y equals log base 4 of x is our base graph. The red graph, and I know you can't see color on your page, but you can see it up on the screen, and also you're told that the blue graph is y equals log base 4 of x, which is labeled, right? So you want to write the equation of the red graph, the one that's above. And if you look at what you're given here, you're given a couple points here, right? The first graph goes through the point 4, 1, and that will transform to the point 1, 1. And so one way you can do this is by looking at it, comparing these points, and you can see that to go from 4, 1 to 1, 1, the x value would have to be divided by 4 or multiplied by a quarter. Okay? It's not just simply shifted up, but the x values are multiplied by 1/4. And so that means it's a horizontal stretch by a factor of a quarter. And then that means that our b value is positive 4. Remember, when you have a horizontal stretch, that is a b value, and the b value and the horizontal stretch factors are reciprocals of each other. So the equation would be log base 4 of 4x. B is what's directly in front of the x. So this can be done by doing some simple logic. Another way you could do this, and we've done this before, again, once you recognize that there is a vertical stretch, and you remember that that means you have a b parameter, so you can put the b parameter into the equation, and then you can say if that graph goes through the point 1, 1, which it does, that point must satisfy the equation. So y will equal 1 when x equals 1. And b times 1 inside those big brackets is b. So you will have 1 equals log base 4 of b. And then to find out what b is, we would convert from logarithmic form to exponential. We would start with the base and cycle through. Remember, the base in the log will be the base in the exponential form. So this will become 4 to the 1 equals b, or b equals 4. So there's another way you could get the b value for that new equation. Okay? This next one, when you look at it, you should realize that there's two things that have happened. The graph has been obviously reflected over the x-axis, and it's been vertically stretched. Okay? If we take the initial point on log base 4 of x, that is the point 4, 1, that was transformed to 4, negative 3. So the x values have stayed the same, but to go from the y value in point 1 to the y value in point 2, you're going to multiply the y value by negative 3. We could write a mapping notation for this one, and we could have done that for the previous one as well, written the mapping notation. And it would be that x, y would map into x, negative 3y, which means that a is negative 3. And our new equation would be y equals negative 3 log base 4 of x. Like the last example, we could also do it algebraically. Once you recognize that it's the A parameter that would be changing, so you rewrite the equation with an A parameter, and then again you use the point 4 comma -3. So using the point 4 comma -3, y is -3 when x equals 4. And log base 4 of 4 is 1. That's asking 4 to what power is 4. If you convert log base 4 of 4 into an exponential expression, that's what it means. It means 4 to what power is 4. The other way you can look at it is if you use a change of base identity. Log base 4 of 4 would be log 4 over log 4. You're dividing something by itself. It gives you 1. So -3 will equal a times 1, or a equals -3. So there's the other way you could determine what the a value is. But again, it starts with recognizing what parameter would be introduced to give you the new graph. So you'd have to realize that, again, you are vertically stretching and reflecting over the x-axis, which an a parameter does both those. Okay? An application involving a logarithmic function. Welding is the most common way to permanently join metal parts together. Welders wear helmets fitted with a filter shade to protect their eyes from the intense light and radiation produced by a welding light. The filter shade number n is defined by a logarithmic function. N equals 7 times negative log t all over 3 plus 1, where t is the fraction of visible light that passes through the filter. Shade numbers range from 2 to 14. Remember, that's what n is, the shade number, with a lens shade number 14 allowing the least amount of light to pass through. The correct filter shade depends on the type of welding. A shade number of 12 is suggested for arc welding. So that, again, that would mean that n would be 12 for arc welding. What fraction of visible light is passed through the filter to the welder as a percent to the nearest 10,000? So we want to solve for t here when n equals 12. We want to solve for t when n equals 12. So I would start this by subtracting the 1 from both sides. On the left, 12 take away 1 is 11. I would multiply both sides by 3 to get rid of the denominator of 3 on the left. I would divide both sides by 7. And this no longer requires the brackets there because the brackets are showing that the negative log t is multiplied by the 7. So if the 7's gone, we don't need the bracket. Before you can get t by itself, I would get the log t by itself by dividing both sides by -1. So you'll get -33 over 7 on the left, equaling log t. And now we want to solve for t, and we would do that by converting from logarithmic to exponential, remembering that this is a common log, no base is indicated, which means it's base 10. So to change, you start with the base and you cycle through. The base of the log will equal the base in exponential form. It'll be 10 to the power -33 over 7 equals t. So that's the exact value of t, the fraction of visible light that'll pass through. We can find out what it is as an actual number by going 10 to the -33/7 in our calculator. -33 over 7. So this gives it to us in scientific notation, 1.93 times 10 to the -5. That means you're going to have 0 point, and then be 4 zeros followed by the 193. That is the fraction of visible light passing through the filter as an actual number. The question says what is as a percent to the nearest 10,000. So to write this as a percent, we would multiply by 100. The first decimal is the 10th, then the 100th, then the 1,000th, then the 10,000th will be the 9. So I write it as a 3, which means the 9 stays the same. So as a percent, it will be 0.0019%. So that's the percentage of the visible light that's passing through the shade filter. Okay? There is a logarithmic relationship between butterflies and flowers. In one study, scientists found that the relationship between the number F of flower species that a butterfly feeds on and the number B of butterflies observed can be modeled by that function. So F is the number of flower species, B is the number of butterflies. Predict the number of butterflies in a region with 25 flower species. So that is F, 25. I'll start though by rewriting the equation. And again, there are 25 flower species, so that's our F value. And we want to solve for B, which we would do by first adding the 2.641 to both sides. And that will equal 8.958 log B. And then we would get the log by itself by dividing both sides by the 8.958. So that gives us that number, 3.086. So we got to round it to write it down. But we keep the entire number in our calculator to solve for B, which again will be done by changing from log to exponential. No base indicated, which means it's base 10. So when we start with the base and cycle through, it'll be 10 to the power, that decimal that's in our calculator, is what B would equal. So we'll use the entire number in our calculator, 10 to the power of the previous answer, to give us the most accurate. So 1217.9. It doesn't tell us what to round to. As long as you round correctly, you're fine. On a diploma exam, it will tell you what to round it to, but this one doesn't. So approximately 1217.9 butterflies. As long as you round correctly, it doesn't matter. On a diploma exam, you will be told what to round to. Okay? Well, you're right, you can have part of a butterfly, but as long as you round correctly, that is fine. Okay, so let's go on to this next section, dealing with the laws of logarithms. remember that logarithms are the inverse of an exponential function. We have rules that we follow when we're working with exponential functions, with exponents. When you multiply powers with the same base, you add the exponents, keep the base the same. Dividing powers with the same base, you subtract the exponents, keep the base the same. One power raised to another, you multiply the exponents, keep the base the same. So we're going to see that there are also laws involving logarithms, and they will mirror what the laws are dealing with powers. So let's see what those laws are. The first one being the product law. First, it asks us to evaluate log base 2 of 4 plus log base 2 of 8. And so you could do this by taking the value of each of those terms. Log base 2 of 4 is asking 2 to what value is 4. That's what it's asking. You could get that by letting equal x, convert from logarithmic to exponential. You can also use the change of base identity if you want, right? That would be log 4 divided by log 2. And the reason the answer is 2, because once again, log base 2 of 4 is asking 2 to what power is 4. That's what it means. And obviously 2 squared equals 4. That's why the value is 2. If you have the newer operating system, you can also do it that way. Put it in there, log base 2 of 4. Calculator will do it. But either way, the answer is 2 to that. Plus, log base 2 of 8 is asking 2 to what power is 8. That's what it's asking. And I'll give you 3. You could use the change of base identity, log 8 divided by log 2. Get the same answer, 3. Or if you have the newer operating system, you can put it in that way to get the answer. Doesn't matter, the answer is 3, and 2 plus 3 equals 5. So that's the value of that first expression. Then part B says, what is the value of log base 2 of 4 times 8? Well, that'll be log base 2 of 32. 4 times 8 is 32. And so this is asking 2 to what power is 32? The answer to that is 5. But you could also get it by using the change of base identity if you wanted to. That would be log 32 divided by log 2. Still get 5. Or if you have a newer operating system, you can put log base 2 of 32 in. Again, you'll get 5. So what do we notice? We notice that when you go log base 2 of 4 plus log base 2 of 8, you get the same answer if it's log base 2 of 32. And if you notice, if you multiply the 4 and the 8 together, you get 32. The bases are the same. They're all logs with the base of 2. And so this leads us to the product law. Log base A of m times n is equal to log base A of m plus log base A of n. And it works both ways. Log base 2 of 32 equals log base 2 of 4 plus log base 2 of 8. Or log base 2 of 4 plus log base 2 of 8 equals log base 2 of 32. Or log base 2 of 4 times 8 equals. Let's write that one out. Log base 2 of 4 times 8 is the same as log base 2 of 4 plus log base 2 of 8. So that mirrors more closely to what's written below where it says the product law. And you can go both ways. You can go from the left to the right or the right to the left. And sometimes you'll have to do it both ways, depending on what you're given and what you're trying to find. So that's the product law of logs. And notice that it mirrors the product law of powers. When you're multiplying powers to the same base, you add the exponents. Here, if you're multiplying logs to the same base, you add the individual logs and keep the base the same. Okay? So now let's see what the quotient law looks like. If you do log base 2 of 16, that's asking 2 to what power is 16? The answer is 4, or you can use your calculator to get it. Minus log base 2 of 8, that's asking 2 to what power is 8? The answer is 3, and 4 minus 3 is 1. For part B, if you evaluate this one, log base 2 of 16 divided by 8, 16 divided by 8 is 2, and log base 2 of 2 is also equal to 1. That's asking 2 to what power is 2. Or that's saying that's log 2 divided by log 2 if you use the change of base. So what do we notice? Well, we notice that log base 2 of 16 divided by 8 is equal to log base 2 of 16 minus log base 2 of 8. So this is the quotient law. The log base a of m divided by n is equal to log base a of m minus log base a of n. Again, it mirrors the quotient law of powers. When you divide powers to the same base, you subtract the exponents and keep the base the same. When you have the log of a quotient where you're dividing two numbers, it is the same as the difference of those two logs with the same base. So you can use these laws to express each of the following as a single logarithm and then evaluate. So there's a couple advantages to this. Obviously, we're going to simplify it, but also in most cases we'll be able to evaluate these without introducing any irrational numbers, because log base 2 of 96 by itself is irrational. That's saying 2 to what power is 96. And the second term is saying 2 to what power is 3. Those two powers would be irrational numbers. But if we use the law of logs first, and in the first case, because you're subtracting logs, right, the law above that involves subtraction of two logs is the quotient law. If you work from the right side of this law over to the left side, we can write it as a single log. This will be log base 2, the base stays the same, of 96 divided by 3. And 96 divided by 3 is 32. And we can evaluate without even using a calculator. This is asking 2 to what power is 32. The answer to that is 5. And you could do it on your calculator if you needed to. By using the change of base identity, you get 5 as the answer. Okay. Question B, you got 3 terms there. So we're going to see that it's always easier if you put the positive ones first. So you're going to put the log base 3 of 27 first, and then I'm going to rearrange those last 2 terms to put the log base 3 of 6, and then I'll have minus log base 3 of 2. In this case, we're going to use both the product and the quotient law. It'll be log base 3 of 27 times 6, and then that will be divided by 2. The 27 and the 6 are multiplied because those two logs are added together. The 2 is on the bottom because you're subtracting log base 3 of 2, so that's using the division law. So now we can write this as a single log by going 27 times 6 divided by 2. That is 81. So it's log base 3 of 81, which is 4. That is asking 3 to what power is 81? And 3 to the 4th is 81. So again, by using the laws of logs, we're able to write it as a single logarithm, and in this case, evaluate. Question C, very similar, except we don't have to rearrange the terms. The bases are all the same, so we can use the appropriate law of logs. Because those first two are added together, we use the product law. Because the last one is subtracted, we use the quotient law. So this will be log base 6 on top. 9 times 8 is 72, divided by 2 is 36. And so this is log base 6 of 36, which equals 2. If you said 6, hang your head in shame. That's asking 6 to what power is 36? That's what that's asking. All right, question D has 4 terms. So we're going to put all the positive and all the negatives together. That's going to be our first step. Put all the positives first, followed by all the negatives. And we're not going to go straight to combining this into a single log. The first 2 terms are no problem. You're adding logs, so that's the product law. That would be the log of 2 times 3. But then you'd have to divide by 6 and also divide by 8. We don't usually divide twice, right, in an expression. So here's what we can do. We can group those last 2 terms together by using brackets. If I group the last 2 terms together by putting them in brackets, there's a negative sign in front of the bracket. So that negative sign that was in front of the log base 2 of 6, that's where that negative sign came from. If I put brackets after that, I've got a negative sign in front of the bracket, which would change all the signs from the step above. This negative log base 2 of 6 becomes positive log base 2 of 6. And the negative log base 2 of 8 becomes positive log base 2 of 8. So now I can use the product law for the first 2 terms. It'll be log base 2 of 2 times 3, which is 6, minus. I can also use the product law for what's inside the bracket. It'll be log base 2 of 6 times 8. Again, because those 2 logs in the bracket are now added together. And now, because I'm subtracting individual logs with the same base, now I can use the quotient law. It'll be log base 2 of 6 divided by 48, which is the same as log base 2 of 1 over 8. Which I think is going to be negative 3. We can do that on our calculator. Using the change of base, it'll be the log of 1/8 in brackets divided by log 2. Yeah, negative 3. So where did I get that from? Here's how. 1 over 8 would be the same thing as 1 over 2 cubed. And I can move the 2 cubed from the bottom to the top. That'll be log base 2 of 2 to the negative 3. And then I actually use the next law that we're going to learn about, which is the power law that says, and we're going to learn about that next, but what it says is that when you have the log of a power, meaning the log of a base raised to an exponent, the exponent can come in front as a coefficient. We're going to see that right away here. So the exponent comes in front as a coefficient. Log base 2 of 2 is 1. It's log 2 over log 2, or 2 to what power equals 2. So that becomes negative 3 times 1. So that's where I got the negative 3 from, before even touching the calculator. So let's prove that right now, that 2 log x is the same as log of x squared. So this is the power law, right? If you have the log of a power, meaning there's a base and an exponent, the exponent can come in front as a coefficient. The 2 comes in front, and it's 2 log x. Okay, so here's the proof. Very simple. Two log x means log x plus log x. That's what it means. And now you can use the product law. You're adding logs with the same base. So you can use the product law to combine them into a single log. Using the product law, it's the log of x times x, or the log of x squared, which is what the right side is. This verifies that that product law is correct, that the log base a of m to the n, you're taking the log of a power, you can rewrite that with the exponent coming in front as a coefficient. That's the power law of logs. So it says first express as a single logarithm, then evaluate. So for question A, the first thing I would do is I would use the power law in reverse. The coefficients can come up as exponents. I'm using the power law in reverse because you can go both ways. Just like the product law works both directions and the quotient law, so does the power law. So this would be log base 2 of 16 to the power a half minus log base 2 of 8 to the power a half. Power half means square root. So now we can say this is log base 2 of the square root of 16. Yeah. And power 1/3 means cube root of 8. So yeah, that should have been 3. The square root of 16 is 4. This cube root of 8 is 2. And now you can use the quotient law because you're subtracting logs with the same base. And you could have done this earlier, but we still would have had to take the square root of 16 and the cube root of 8. So this will be the log base 2 of 4 divided by 2, or log base 2 of 2, which is 1. So by using the laws of logs, we didn't even have to touch a calculator. You could certainly use a calculator to check your answer, though. Putting in the original expression, 1/2 is 0.5. 0.5 of log base 2 of 16 minus 1/3, which I have to put that as a rational number because it's a repeating decimal, log base 2 of 8. Gives you the same answer, 1. Okay? Question B again. Before we can write these as a single log, we got to get rid of those coefficients. We got to use the power law in reverse. The coefficients come up as exponents. So this will be log of 5 squared plus log of 2 squared. That'll be the log of 25 plus the log of 4. And now because we're adding logs with the same base, we can use the product law. This will be the log of 25 times 4, or the log of 100. And what does that equal, MJ? You were what? Earl? What does that equal? Want to bet a pop on that? Remember, common log means base 10. Yes, Samantha? Because that means 10 to what power is 100? It's okay, I know basketballs are a little slow, so basketball players, I should say, a little bit slow, so we all understand. Oh yeah, what? Excuses, excuses. Doesn't change the facts. Academically, basketball players struggle. Okay. Question C. Again, we'll use the power law in reverse to bring those coefficients up as exponents. So that first term would be log base 5 of 2 cubed minus log base 5 of 8. There's no coefficient on that one. So this would be log base 5 of 8 minus log base 5 of 8. If you subtract something from itself, what do you get? Now, if you use the law of logs, using the quotient law, it'll be, and we're using the quotient law because it's subtracting the logs, It'll be log base 5 of 8 over 8, or the log base 5 of 1. So how does that equal 0? Yeah. Yeah. That's right, because this is asking 5 to what power is 1? Anything to the power 0 equals 1. That's why it's 0.
So anything that has a base, anything with 1 has a base 1.
The base isn't 1, the base is 5.
Or
The argument is 1. Yes. If the argument is 1, if you're taking the log of 1, no matter what the base, the answer will be 0. Okay. Question D. We'll again use the power law in reverse to get rid of the coefficients. So 2 log base 6 of 9 would be log base 6 of 9 squared, or log base 6 of 81. At the same time here, I'm going to put the positive logs first, put the minus 1 last. And that negative 3 log base 6 of 3, the coefficient of 3 comes up as an exponent. 3 cubed is 27. And now I will write as a single log by using the product law first, because you're adding the logs together, followed by the quotient law because you're subtracting. Log base 6 of 27. So now we can find out what our argument is in simplest form by performing those operations, and you'll get 36. So this is log base 6 of 36, which equals
2.
Very good. You can pick your head up again, Sant. Be proud. Yeah. So these ones can be checked on the calculator again by just putting the expression in. So if we check that last one, if you don't have the new operating system, you have to write them all using the change of base identity. So that first one would be log 9 divided by log 6. So log 9, close the bracket, divided by log 6. Close both brackets. Minus 3 times, that'll be log 3 over log 6. So open a bracket, log 3 divided by log 6. Got to make sure you close the bracket each time you do the log of a number. Plus 3, and if we're using the change of base identity for that last term, it would be log 27 over log 6. Whoa! What did I do wrong? 2 log 9 divided by log 6. Let's see here. Oh, it should have been minus 3 log. That should have been minus. Still not right. Check these again. So that is minus, that's correct. This one should have been plus. Check them all here from the start. 2 log base 9 divided by log 6. So that one is right. Minus 3 log of 3 over log of 6. Okay, so I think I went from the top line down to the bottom line, the second line when I was putting this in. It should have been, actually there is no coefficient there. That last part is log 12 over log 6. I'm keeping everything from that top row. One more time, let's check it. Log 12. Oh, gotta close the bracket after the log 12. There we go. Okay. Playing here all week, same time. So these next ones you can't check on your calculator because they have variables in them. But you can still use the laws of logarithms in order to simplify, which is what it asks us to do. Express as a single logarithm. So like we did before, when you got a combination of positive logs and negative logs, we'll put all the positive logs first. There are no bases indicated here, which means they're all common logs, which is base 10. The other thing I'll do is that 1/2 log a, I can write as log of a to the power 1/2. The first negative log is minus 5 log e, which is minus log e to the 5th, minus log of a squared. So again, this was a d. So like we did before, because we never have two divisions in one expression, I'll use some brackets to group those last two terms together. If I add brackets in there, group those last two terms together, there's a negative sign in front, which will change all the signs inside. And now I can write this as a single log. It'll be log of b times d times a to the 1/2 all over e to the 5th a squared. And I can simplify a little bit because I have a factor of a on both the top and the bottom. So we would subtract the exponents and keep the base the same. When you go 1/2 take away 2, that'll be negative 1.5 or negative 3/2. We move it to the bottom though, so it becomes positive 3/2. And so there we've expressed it as a single logarithm. Same thing for question B. I would put the positive logs together. Now that 4 times log of the 5th root of p, that would be the log of p to the power 4 over 5. Right? It's the 5th root, which is the denominator. Whenever you have a radical, you can write that as a power with a rational exponent. The denominator tells you what root it is. It's the 5th root, so the denominator is 5. The 4 would go up as an exponent, so it's raised to the power 4. That tells you the numerator. Minus, you've got 3 log n, which is the log of n cubed, minus 2 log p, which is the log of p squared. So again, we will group those last two terms together using brackets, which will change all the signs inside the bracket. And now we can write this as a single log using the appropriate laws. And because you have powers of p on both the top and the bottom, you can simplify those. When you're dividing powers, you subtract the exponent. So it's 4/5 take away 2, which would be 10/5. 2 is 10/5 with a denominator of 5. So 4/5 take away 10/5 is negative 6/5 but you move it to the bottom so it becomes positive 6/5. And so there's the answer expressed as a single log. Okay? So this assignment, you're going to hand in, use the laws of logs to write each of the following as a single log and then evaluate. So write it as a single log first. Use the appropriate law to do that. You must write it as a single log first and then get your answer. You can always check by putting the original expression in your calculator. Right? There are no variables for any of these. They're all, the arguments for those first ones are all numbers, so you can get an answer. But for those last two, can't check those in your calculator because they involve variables. Okay, so again, this one is due for marks.